Awesome. I'm gonna give a minute before we start, but wanted to say, hello everyone, and welcome to this week's Arise community paper reading. My name is Dat, and this is Sally Ann, and today we will be talking about GLORA, also known as Generalized Low Rank Adaptation, which is used in fine-tuning large language models. But before we do that, we are going to quickly introduce ourselves. So my name is Dat No. I am a ML solutions architect here at Arise. I work closely with technical teams, ML teams at other companies. I've been a data scientist for a long time, built a lot of kind of models, built a lot of ML infra as well. But really excited to have you here today at our community paper reading, and I'll let Sally Ann introduce herself.
Hey, I am Sally Ann. I'm also a machine learning solution engineer here at Arise. My background's in deep learning, so spending a lot of time with deep learning models, embeddings, that's right up my alley. So super excited to be presenting our paper today.
Awesome. Thank you so much, Sally Ann. All right, so what are we going to talk about today? So really quickly, I'm going to go over today's agenda. And so for today, we're excited to walk you through we're going to go through a brief overview of fine-tuning. What does it mean? What does it mean in the context of LLMs? And generally, how are LLMs trained? Then we'll do a review of all the work previous that was done before kind of GLORA and all the kind of foundations that it was built on, things like, parameter efficient fine-tuning methods. And then we'll go kind of deeper into the GLORA paper, kind of the methodologies, what are the kind of findings that came out. And last, while the paper is extremely mathematically dense, we kind of broke it down in a way that we hope even kind of the average person who maybe doesn't work in the LLM world can kind of understand. And so we'll leave you with some main takeaways and some nuggets to take home with you. So before I guess we get into the paper, I think it's important to give folks kind of some background and some kind of context about how LLMs are trained and how we get them to do, what they do. So how exactly are LLMs trained, and what is the current recipe? So this is kind of subject to change as the field is, constantly and rapidly changing. But so far, the recipe looks something like this. So roughly speaking, we have about, we have 4 major stages to how do we get from scratch a large language model all the way into kind of all the stages of kind of the most mature version, which is all the way through kind of reinforcement learning. And so we have these 4 stages. So we have kind of pre-training, we have supervised fine-tuning, which will spend the bulk of the time kind of talking about this. But I wanted to kind of, set the context for, the larger kind of picture here. We will be focusing on this stage, but just want to give folks kind of a higher level view of what it actually takes. So we also have reward modeling, which leads into, reinforcement learning. So if you ever hear the acronym RLHF, it's referring to these 2 stages. So in each stage, we have a data set that powers that stage, right? And we also have an algorithm or an objective or the thing that we're kind of optimizing in each stage. And from each stage, we also have kind of a resulting model. You've heard things like base model, fine-tune model, RLHF model, things like that. And then we also have some notes about, kind of like how, some notes of like, how long does this take to train, things like that. What's the scale of in context when it comes to all 4 stages? And so, the first stage that happens is the pre-training stage. This is the first step, and it's really where most of the computational work basically happens. This stage is 99% of the kind of compute or training time in kind of when it comes to all 4 stages. And so really quickly, when we talk about like, why does this take so much time? Well, this is where we deal with internet scale data. with thousands of GPUs in a supercomputer and months of training. That's what it really takes to get what's called a base model, or this kind of pre-training stage. And we learned in another paper reading that this is where most of the skills and capabilities of an LLM really come from. So like how to read, understanding semantics, context, things like that. So from this pre-training stage, we get what's called a base model. And so that kind of comes out of here. So when you hear somebody say base model, it's generally from kind of the pre-training stage. And so now the other three stages, by comparison, are smaller in terms of computational time. They take like a few GPUs and take along the lines of kind of hours and days to perform, rather than maybe months to train this one, kind of in the pre-training stage. And so when we look at the next stage, which is supervised fine-tuning, the question you should have in your brain is like, okay, so why do we need to fine-tune our base models? So when we go from here to here, what's the whole purpose of fine-tuning and why do we do it? Well, base models are not assistants. Base models just try to guess the most likely next set of tokens. They're not super helpful in their own right. And while you can trick these base models into tasks by rewarding or prompt engineering kind of the input text, it's not the ideal solution, and it doesn't always work out super well. Just as an example, if you took a base model and you said, hey, write a poem about bread and cheese, it actually wouldn't write a poem about bread and cheese. It would try to assume the next likely tokens, which is like, write a poem about this, write a poem about that. So just realize that base models need some sort of kind of fine tuning. So this is where this stage really comes into play. The first thing that we need to do for kind of our SFT stage is to really collect a small but high quality data sets. This is usually done by human contractors or humans that collect these kind of ideal prompt, and these prompts, they're given prompts and they produce an ideal response. The order of magnitude for these types of examples ranges on tens of thousands, so not quite internet scale, but definitely hard data to come by. And so the idea behind fine-tuning may look like this. So this data that's kind of training, or kind of the data set that we're fine-tuning on, may look like this. So step one is a human is actually given a prompt. So this prompt could be, hey, write a short introduction about the relevance of the term monopsony, etc. So a human on the other end is also given, step two, this very extensive and intensive labeling instructions, where they're tasked to be, hey, be super truthful, be very helpful and harmless, for example. So they write this response, and this is really the data that the fine-tuning is done on. And so we're not going to go through the rest of the kind of stages, but for the most part, I just wanted people to have kind of context of what we're covering, and what's the data that it looks like, and just a larger context of fine-tuning. So I'm going to let Sally Ann share her screen next.
Great, thanks, Dat. Cool. Let's get into the paper. I think Dad did a great job of laying the groundwork for what fine-tuning is, and that's really what GLORA ties into. So one thing I do want to mention, that this paper is brand new. This was just released a few weeks ago. I think it was no more than 2. So we're in very early stages. I'm sure we'll see this paper be taken, improved upon, and then also probably morph into even more fine-tuning methods. So the first thing that this paper actually does is it covers other parameter efficient fine-tuning methods that exist prior to GLORA coming out. And GLORA actually draws from each of these in its implementation. So we need to cover each of these at a high level to understand, which the paper does itself. So the first of which is visual prompt tuning. So this is inspired by prompting in NLP. VPT introduces a small amount of task-specific learnable parameters into the input space while freezing the entire backbone of the transformer. And so you might be thinking, prompt, is that prompt engineering? Dad was just telling us about that, but it's a little bit different. So VPT uses what's known as soft prompts, and these are generated by a small set of learnable parameters. And this is in contrast to prompt engineering, which uses these hard prompts, which are manually provided. So that's the main difference between the two. And so what these are is they're continuous embedding prompts that are introduced into the input space. You can see here the P0, those are going to be the injected prompts. And then what we're going to do is they're going to be updated during fine tuning, but the main body of the transformer, as you can see in these visualizations here, are kept frozen. And so this method has two variants. So this one on the left, this is what's going to be known as shallow. And this is when it's only, I'm sorry, I mixed that up. On the right-hand side is the shallow, and that's when it's only introduced into that first transformer layer. In VPT deep, that's when we're going to have it between both the input layer and then between the various transformers. So basically we're having those prompts at every transformer layer input. Cool. So that's VPT. The next one it introduces is Adaptformer. So this introduces a parallel learnable branch into the two linear layers. And so it has this kind of like plug and play bottleneck module called AdaptML. So that's what this piece is here. And if we explode that out a little bit more, it has these two branches. So the first branch is exactly the same as the original MLP block, which is multi-layer perception. Also, it can be called the forward feed network. And so the other piece of this is this lightweight module that's introduced for the fine tuning. And so this bottleneck structure limits the number of parameters that are included, and then it has this ReLU activation. So we have the up projection layer, the down projection layer, and then the ReLU activation layer. And so during fine tuning with Adaptformer, only the new added parameters are optimized. That means the rest of the model parameters are kept fixed. So again, we're decreasing the number of parameters. You're going to hear me say that probably a lot as we go through these, but that is pretty much the overall goal of parameter efficient fine tuning, is to reduce the number of parameters that we need to fine tune. LoRA. Okay, so you might have come to our talk a few weeks ago. We did a whole paper reading on LoRA. If you haven't checked it out, I highly recommend it. But LoRA basically borrows from that linear algebra concept of matrix rank and decomposition. So the key hypothesis here is that while these models are very large, they have millions or even billions of parameters, they have intrinsic low dimension and the weights have intrinsic low rank. So what this means is we only need a small subset of parameters. So we take our weight updates here and we're actually going to break it into smaller low rank matrices A and B. And so during the fine tuning process, the model is going to add these low rank matrices to the pre-trained weights, and then we're going to keep the rest of the weights frozen. So we'll only train on these, and then the selective updating essentially makes it so the fine tuning process, again, more efficient, as we're only going to focus on the ones that are the most impactful.
So one quick question I had for you, Sally, is, you know, why is PEFT or parameter efficient fine tuning, like why is it important? And, you know, what happens if we didn't use PEFT or like these methods?
Yeah, so as I mentioned a bit earlier with the concept of LoRA, is that these models that we're looking to fine tune have millions or billions of parameters. That takes a lot of time, a lot of resources, a lot of memory to carry out that process. So data scientists, MLEs, are trying to figure out a way that they can fine tune these models to their specific tasks without having to take on the burden of fully fine tuning. And that's really why they're leaning on these parameter efficient fine tuning methods. I think we're going to see a bunch of these start coming out because people are just going to be getting more and more creative to figure out how can we get these models trained for our task as fast as possible with using as little resources as possible.
Got it. Got it. Yeah, definitely. And then kind of why we're focusing on this kind of visualization here. So like just for like context sake, I think like if we used something like Atom, for instance, with like GPT-3, 175 billion parameters, I think LoRA, like for instance, LoRA can reduce the number of trainable parameters by 10,000 times when compared to Atom. So when we think about why this is important, when companies or folks need to build a, their own kind of LLM, definitely reducing costs here is super important. So thanks for going over this. I really like this visualization. And when we kind of review some of the methods pre-LoRA, either they kind of added, if you can look at the kind of, you see kind of the pre-trained weights here, which I think you'll get into, but I think if we look at how the technology has evolved, LoRA is awesome because it doesn't add latency, like I'm sure you'll go over, but also it, like I said, it doesn't add latency and it just makes things just cheaper. So I really like this kind of visualization because you kind of leave the blue part alone. That's kind of the pre-training phase that kind of we talked about. And really the only thing you're adjusting is A and B, right? Cool.
Yep. Perfect. Yeah, so we can get a little bit more into what these pre-trained weights are. And so usually, you know, as you mentioned earlier, Dat, like when we're fine tuning, we need to update these weights constantly when we're doing fine tuning. But with LoRA, we're really going to pass the data into both and then just going to be adapting A and B over time to get those optimized parameters. And so we're keeping those pre-trained weights frozen and only updating the right side of this visualization here. And so we're defining a rank. It's not really quite well visualized in this, but rank is a really key component to LoRA. It goes back to the, again, principle of linear algebra that, you know, all matrices intrinsically have low rank, meaning you can reduce it. So if we choose a rank 1, which is pretty common to do, it can then only have to have a matrix that essentially is, it would be D by one of A would be D by R and then B would be R by D. So they're going to be much, much smaller and thus much quicker to retrain or pre-train. Make sense?
Yep, that makes a lot of sense.
Cool. LoRA is a good one. It's quite cool to play around with too. If anybody hasn't played around with LoRA, I definitely recommend doing that.
Yep, and feel free to, we also posted the LoRA talk on our kind of, I think our paper readings. So if you did miss LoRA, there's always a chance to go back and watch it.
Also kind of foreshadowing ahead, there's also going to be a blog post coming about LoRA, so keep your eyes peeled for that one as well. That's a really cool fine-tuning technique. Cool, let's get to another one here. So next we have scaling and shifting features. So as you might guess, we're going to scale and shift features after each MLP, which is the multi-layer perception layer, as well as the multi-head attention layer, as well as the layer norm module during training. And so we're also going to perform re-parameterization during inference. So unlike the other approaches, that's the set of parameters that we use to fine tune when we use scaling and shifting features, the number of parameters remains the same. So it doesn't matter what task we have, the number of parameters is going to be the same. And so it makes it easier to fine tune for like multitask learning. So I think that's really important to know about this particular fine tuning method, is it's pretty different in that respect versus the other methods. And so for this process here, you'll notice that there's this SFADA that's inserted. And so what this does is it performs the linear transformation for this parameter efficient fine tuning. And so after each operation in the network, we're personally going to inject these, and then that structure will perform a dot product on the scale factor and then sum it for the shift factor. So that's kind of what's happening down here. So the approach is designed to have independent scale and shift factors, so that gamma and beta down here to represent the distribution of the whole downstream data set. So that's a super important. We're going to come back to this when we get into GLORA. Next one, fact or factor tuning. Basically, this one, the fundamental idea is to represent the change to the weights of a pre-trained model using compact factorized representation rather than needing to store that full set of weights for each downstream task. So it's proposing to use this tensorization decomposition, which basically means the weights of the model are tensorized into the single 3D tensor, and their additions are then decomposed into lightweight factors. And so during fine tuning, only these factors are what's going to be updated and stored. Last but not least, RepAdapter. So this simplifies the structure of the adapter into a linear projection layer. So it's incorporated into the near projection weights via the matrix multiplication. So there are two common ways to do this. So you can see these here are going to be the RepAdapter here. And so you can see that there's two places it can go. It can either go into the multi-hit attention layer, or it can go into the forward feed network, or the also called the MLP, depending on which paper you're reading. And so it inserts these lightweight networks into the pre-trained models, and then the additional parameters will just be re-parameterized to the nearby projection weights after training. So this is what the re-parameterized layer is going to look like here. So I'm going to pause here. Let's check out, are there any questions? We just went over quite a bit of material. We can link the papers to these as well. Each of these comes from its own paper, but now GLORA is going to draw upon them. Yeah, any questions on these ones?
Yeah, so let's say I'm not a math person. And if you could like TLDR kind of a lot of the mechanics here, how would you kind of describe just a really short summary of like what are these like kind of it's a lot of matrix algebra, but like what does this allow us to do? And you don't have to go through all of them, just like TLDR, why is this useful? And if for folks who don't understand the math, if you could maybe put it in a way that they could understand.
Absolutely. What I'm going to do is I'm just going to give a high level, the main takeaway for each of these. So for visual prompt and prompt tuning, the main takeaway there is we're introducing those small amount of task specific parameters. That's the main thing there, is we're going to introduce these small parameters. That's really all it comes down to, is these little extra parameters interjected into these different layers. For AdaptFormer, this is going to be a little bit more complex, but basically here is we're going to create two parallel branches for this adapter. And so what we're going to do again is keeping that original one, and then we're adding in this new small amount of parameters that we're actually going to adjust. So the unique thing here is that we have these linear branches. LoRA, we kind of went into this one in detail really quick. So concept is, yeah, we can skip this one, but it's the matrix decomposition is what's really powerful about LoRA, and the fact that it's playing on intrinsic rank.
Yep.
And then for scaling and shifting features, I think the two main things you need to account for here is the scaling and shifting of the features, but also the re-parameterization during interface or inference. That's super important there. And then for fact, this one's, I think, probably one of the most math heavy. There's a lot of technical things that come under, but the real thing that you want to keep in mind is we're going to tensorize this into that single 3D, which is more efficient. And then we're going to be able to decompose these later on. And then for this one, for RepAdapter, this is kind of similar to the one we just covered. I think that the main thing here is it's going to simplify the structure of the adapter to just be this linear projection. I think that's probably the most important takeaway from RepAdapter.
Gotcha. Awesome. Thanks so much. It's super useful.
Of course. All right, so GLORA, we've arrived. We've just covered 6 other parameter efficient fine tuning methods. We're really now getting to the main bread and butter of today's presentation. And so this approach really serves as a subset of all those other prior solutions that I discussed. So it can be reduced at any point to any of the previous methods by simply setting the specific tensor to 0. And it's designed to both fine-tune the weight space and the feature space. And so it addresses some of those limitations that you might that might occur with the previous methods. So another really big part of GLORA is the fact that it can be easily expressed as a unified mathematical equation. So here, which ties the visualization together, is the equation on the top. And so you can see here that we have W sub naught plus W sub naught times A plus B times X, which is going to be our input. And then we can easily then add C times W naught plus D BW sub 0 plus E plus B sub W. Quite a mouthful. I didn't even get it right, but that's fine. You get the point there. So let's break down this a little bit further. So what do A, B, C, and D even mean? Well, these are our trainable support tensors for the downstream tasks. And so these can take on different forms. So they can either be scalars, vectors, low rank decompositions, hint, LoRA, or they can just be none, again, so that we can revert back to one of the previous methods. And so during this pre-training, or I'm sorry, fine-tuning phase, W sub B and sub 0 and B sub 0 are going to stay frozen. So we're only going to be fine-tuning these orange blocks here. So the A, B, C, D, and E. And so each tensor will really serve as for a specific function. And so A is going to typically scale the weight, B will scale the input, C is going to have functions very similar to VPT Deep. So again, focusing on VPT Deep, not shallow. So we're going to interject those prompts at every layer. And then D or E are going to be used to scale and shift bias respectively. So what this allows you to do is it allows for an expanded search space without increasing the number of parameters significantly. This leads to faster convergence due to weight sharing across these different subnets. And so that's really the technical side of LoRA. That's the math. That's what it looks like. And you're probably thinking, what does this all mean for me? Why does it matter? That is going to get to that. But there's just one little thing I want to cover before we do that. And that's going to be experiments and results. And I think that's pretty important. So if you read the original paper, it is focusing on like vision transformers, but recently they've been doing work with these large language models. So this table here is actually from the GitHub repo that they have just recently updated. And this is showing the performance on language tasks with pre-trained llama and using that alpaca dataset for fine tuning. And so you can see here that LoRA has way better performance compared to the other, not only the base train model, but also when using LoRA. So you can see here, on average, it comes in about 50.7. That's quite a bit higher than the other methods here. So in the paper, there's a lot more experimental results. They did their job in vetting this, testing it. It does have significant superiority, really, in a parameter efficient transfer learning. They do few shot learning as well as when it's domain generalization. So they really tested this out and saw superior results. And even the smallest GLORA model outperforms all existing methods by a substantial margin. I think that's really important because there's been a lot of talk where these models are so powerful because they're so big. And when we're using these parameter efficient fine tuning methods, we're seeing that these smaller fine tuned parameters are actually outperforming when you fine tune every single parameter. So not only are you saving money and saving time, but you're actually getting better performance, which I think is pretty cool. All right.
Awesome.
Cool.
Great overview. Definitely super awesome that Sally Ann knows the math. If you ever want to talk to her about it. So really quickly, I'm going to share my screen, come back. And so like Sally Ann was saying, yeah, GLORA does perform super well. And we kind of want to understand, if I had to TLDR this, we have a more complex architecture when it comes to fine tuning, and that allows us some certain advantages. So really quickly, why does this matter and what should you be thinking about really? So let's say you work for a company and you need to fine tune a model. Well, the things that you should really consider are, how much is training going to cost? How do I optimize that, right? And, which fine tuning method is going to afford me the best performance? Because at the end of the day, that's super important. Is this fine tuning method going to increase latency for my generation? I think that's really important. Sally, is there anything else that you would add to that as far as like when we zoom out to actually deploying this? I think cost is one, latency is another, and then performance. Anything else you would add?
I think those are really the main ones that come to mind when I'm thinking about this. I think training data, oftentimes, you kind of touched on that, is something that takes into consideration, and maybe the complexity or what the specific task is that you're trying to fine tune for. I think those are other things that you might want to take into consideration.
Awesome. Yep. Totally agree. All right. We have about 12 minutes left. So quickly, we're going to do really like a high level overview of where the progression has been made from LoRA to GLORA. And so the first one is really model flexibility. So this is kind of a TLDR on the important parts going from LoRA to GLORA. So model flexibility and efficiency. On the left-hand side, you can see LoRA. On the right-hand side, you can see GLORA. You can see a much more complex architecture and a lot more moving pieces. But so how LoRA worked is we freezed, as Sally Ann, pre-trained model weights and injected low-ranked, matrices, and we can kind of change that. GLORA, if you look at the architecture, is just much more complex. So why is this important? What allows us more flexibility and allows us to, especially GLORA, to adapt to a variety of tasks and data sets. Meaning, if I'm fine tuning on a specific task or data set, if you have more levers, it allows you kind of more adaptability. So an example here is this is achieved using kind of this kind of prompt module, and of course, like the sharing of weights and immediate activations. But wanted to highlight that. The other one, TLDR that Sally Ann did cover was parameter adaptation. Why is this important? Well, the layer-wise approach really allows us to make more kind of fine-tuned adjustments. So like a really good like metaphor I like to use here is like, imagine you have like a radio where you can turn one knob and it affects like the treble and the bass. Well, with GLORA, now you have individual knobs, so you can, really determine what kind of sound you want to hear, and it becomes extremely useful. Like Sally Ann said, the unified mathematical formula. And so the way I kind of describe this one is like, with like LoRA, you have kind of like a fixed blueprint for kind of your house. You can change like some of the interior decorations, but the main structure is still not changeable. But with GLORA, for instance, you kind of have this modular home design where you can kind of rearrange the rooms and add a second story or convert. This transitioning from kind of a fixed blueprint to a more flexible design, and you're starting to see the themes like LoRA is obviously more flexible, but obviously more complex. You can build a better home that kind of suits your specific needs. So kind of the same as kind of before. The Re-parameterization strategy, kind of a good metaphor I like to think about this is like, it's for like LoRA, it's similar to painting a picture using only primary colors. And with GLORA, it's like having your full palette. This allows you to have more nuanced work or more nuanced kind of parameters. And so this shift is kind of important in the fact that you have just a larger solution space that you can solution in, if that makes sense. And then really the last thing is some considerations. So the paper is not perfect, meaning it's not the ultimate method. There is a kind of an evolutionary search aspect to this. So instead of having to manually do some hyperparameter tuning, there's kind of you can call it a smart search, but it takes a lot of time to kind of do it. So and it was a little confusing at first when I was reading the paper, but there's an increased duration for this search process, but the overall kind of fine-tuning method with GLORA is actually less computation and more efficient. But this one particular step did increase in time or in training time. Like Sally Ann did say, this is a pretty new paper. There's relatively this is a new methodology and there's unexplored domains. So this method is still in its infancies and there's a lot more to kind of exploration to be done. There's adaptability to convolutional layers. So yes, this method can be applied to other fine-tuning, other modals like computer vision. And of course, when we look at, there's more increased complexity, meaning if you're doing this on your own and you're wondering kind of how to do this, because it's brand new and there's more complexity, chances are you might get stuck somewhere. So just realize that. And so these are the key takeaways. I hope you got a lot out of this. I hope the kind of high-level overview and the importance of why fine-tuning is essential to kind of any useful LLM. We built upon kind of LoRA and kind of the methodologies there to get us to kind of GLORA. And then we kind of talked a little bit about the math and why these things are important. But the real takeaway is that there's a lot of work to be done and much more research to be done in these cases. I don't think the final, architecture of this it's ever going to be complete, but I think this will get more and more complex and smarter kind of over time as folks figure out a way to fine-tune their models. But so that's what we have for GLORA. I'm going to pause here really quickly. Sally Ann, is there anything else you wanted to add?
Yeah, I actually have a question that we can kind of discuss that I think is interesting is, LoRA was initially written in 2017, and it only recently really became popular for these LLM use cases that really works for any model that has weights, but with LLMs, it's been really popular. Do you think GLORA is going to kind of catch up and it'll be switched out and data scientists will be reaching for GLORA before they reach for LoRA?
Yeah, that's a good question. I mean, if you follow like kind of the state of LLMs, you'll realize it's not monthly that a new piece of news happens, it's weekly or daily. Maybe it'll get to hourly, but I think people, I probably will guess today there's somebody doing research on better fine-tuning methods than GLORA, or building upon some of the, I think having all those layers was like kind of a game changer inside of GLORA.
Yeah.
And so as folks start to innovate and think of new ways to shift levers so that we can train more intelligently, rather than just kind of bulk train, you know what I mean? That it'll change, but curious to know your thoughts as well on that.
Yeah, I think it's so new, it's hard to say. Because if you look, the paper is available, but you don't really see that many other papers like taking it, building with it. So I think it's very early. Once more people start experimenting with it, I think we'll have a better indication of how things are going to go. But I'm seeing people use LoRA more commonly than I am seeing people use GLORA right now. But since the research group that had put this paper out has now kind of shifted into the language space, I think maybe that's going to change things too.
Yeah, totally. And I think it's risk reward too. It's like if you have like a bunch of people working on the same thing, well, you can always go ask for help. But with kind of newer methodologies, you're kind of on your own and kind of primed to figure it out yourself. But definitely excited to see more developments happen in the community.
The good news is they both have repos. So if you want to try it out, they've got a place for you to start. They both have GitHub repos, and I know Dat linked the LoRA one, but I can throw in the GLORA one now. We did just get a question if you want to take that while I'm pulling up this link, or I can take it in a second.
Yeah, so Chris Murphy asked, so is LoRA and GLORA both multimodal, fine-tuning, images, etc., or are they both just text? So what I read is that they can be applied for both modalities, but I think specifically for LoRA, it was mostly tested on text, but I could be wrong there, but I don't know, Sally Ann, any thoughts there?
Yeah, so they're both multimodal. I think LoRA, the benefit there is it actually can be kind of beyond that, as like I mentioned earlier, it can be used for any model that has weights essentially, whereas GLORA has got a little bit more to it, that it's going to work more with the transformer-based architectures. And yes, GLORA was originally done with images, and I think LoRA was originally done with text, and then they both kind of crossed over and realized that they could do both. But yeah, I totally agree with you, Dad.
Yeah, in the section of the GLORA paper, they said they haven't done any work with convolutional neural networks. So like Sally Ann said, I think we will see developments in the computer vision space with GLORA. Awesome. Well, thank you so much for everyone who attended. Thank you so much for the questions. We're really excited to have you at our paper reading. This will be, on our website for kind of recording. But really excited to have you all, and we look forward to the next paper reading. Thank you so much.
Thanks, everybody.